So far in this course, we have talked about two kinds of basic simple machines, inclines and pulleys. An incline can help us save force. Instead of lifting this cart straight up by applying a force that overcomes mg, I can pull it up the incline and only have to overcome mg's component along the incline, the mg sine theta. mg sine theta is less than mg, so I get to save force. A simple machine allows us to save force, but we cannot save work because energy is conserved. If we want to increase the gravitational potential energy of a cart by 10 joules, we have to spend 10 joules, no less, whatever method we use. Let's compare the work required to lift the cart straight up versus along an incline. The work is force times displacement times cosine the angle between the two. If we lift the cart straight up, the force we have to exert is mg to overcome the downward mg. The mg goes upward, displacement is h upward, so the angle is 0 degrees. Let's look at the incline. For an incline, again, it's force times displacement times cosine the angle between the two. This time, the force you have to overcome is the mg sine theta. So your force will be up the incline, mg sine theta. Now, the displacement is not h. It's the hypotenuse of this right triangle. Since the sine theta equals to the opposite side h divided by the hypotenuse, that means this distance traveled, the hypotenuse would equal to h divided by sine theta. So the displacement here is h divided by sine theta. And then, of course, the force and displacement same direction, so it's cosine 0 degrees. And so both of these is 1. And the sine theta, of course, cancels, so you can see the work done is the same. We cannot save work. If your force changes by a factor of sine theta, then the displacement will change by a factor of 1 over sine theta. When we save force, we end up traveling a longer distance. Of course, if we have to find the work done in either cases, we can also use the conservation of energy, which says the work done by the non-conservative forces equals to the change in total mechanical energy. In both cases, the non-conservative force that's doing work is the force from me. And the change in mechanical energy is delta K plus delta U. Since we're looking at the work required, we're not changing the kinetic energy of the cart. So the change in total mechanical energy is just the increase in gravitational potential energy. The cart got higher by height h. So the increase in gravitational potential energy is mgh. So that's the work. The work done is turned into the increase in gravitational potential energy. Now let's look at a pulley problem. We're using this pulley system to lift a box mass m by a height h, find the required force to lift the box and the required work to lift it by a height h. Let's first find the required force. In this case, all this is connected together. They move together. So we can treat all this as one object. And we're going to treat the pulleys as massless. Therefore, the entire thing over here has a mass m. So the mg is being held by the same string 1, 2, 3, 4, 5, 6, 7, 7 times. So you have mg going down and 7 tensions going up. So each tension is mg divided by 7. So the required force is mg divided by 7. which means we get to use this pulley system to save force. We only have to use 1/7 of the weight to lift this box. What about the work required? That will be force times the displacement times cosine the angle between the two. The force we have to exert is mg divided by 7. Now the displacement is not h. It is 7 times the h. Because if I want the box to go up by a distance h, every string has to be shortened by a distance h. So I'll have to pull away 7 times h. So my force's displacement is 7 times h. And the force's displacement and the force are in the same direction. So the work here is positive cosine 0 degrees. And this is mg times h. If we get to save force, so the force is 1/7, then the distance will be 7 times as far. Or, of course, I can also use conservation of energy. The work I do is going to turn into the increase in mgy, and that's mg, and the height change is h. Here we have a pulley system that is the same as the one in the problem. The weight hanging here is a 1 kilogram, 10 Newton weight. See, there are 1, 2, 3, 4, 5, 6, 7 strings. 7 strings supporting the weight. So I only have to exert 1/7 of the 10 newtons to lift the 10 newtons weight. By the way, the reading you see here is slightly more than 10 divided by 7, which is 1.43 newtons. Why do you think that is the case? Because the pulleys and the string have mass. So the real weight here is a little more than 10 newtons. Since I get to save the force by a factor of 1/7, I have to travel longer distance by a factor of 7. See, now the weight is at this marking right here, and the hook of the scale is here. When I lift, can you see that the scale has to go up a lot more than the weight? 7 times the distance to be exact. When I watched the last segment of the video, I saw that I held the scale sort of like this with a slanted string. So if you answer the slanted string to my question on why the scale read more than 10/7 or 1.43, you're correct also. See, pay attention to the reading. If I slant the string, the tension reading will be higher. Because when the string is slanted, only the vertical component of the tension is helping to support the weight.